Okay, this is going to be our second video on rotational motion. So in the first video, we spent some time talking about well, I guess we spent some time defining angular acceleration. We also reviewed the definition for angular velocity, and then we kind of talked about how we could relate linear and angular quantities. At the end of the video, I pulled up that nice little table from the textbook where they summed it up pretty well. I've rearranged things here, and here we have sort of a set of equations that lets us really relate our linear quantities to our rotational variables. Okay, and so we're going to use these ideas to now translate a lot of the work that we did in the very first module that we did on kinematics into their sort of rotational equivalents. Okay, and so if we think back to the first module, I think at the end of maybe the third set of notes and video in that module, I wrote down the sort of collection of equations that we see here, equations 4 through 8, where we see sort of all the tools that we use to do our calculations in 1D kinematics, right? And using these translations here, this sort of rubric that lets us translate from linear to rotational sort of language, we can translate all these equations into useful similar equations that let us do calculations in rotational kinematics, and so that's sort of the title of this section, right? So kinematics of rotational motion. So we're going to be doing calculations, well, kinematic calculations for rotational systems, for rotational motion. Okay, and so let's remember sort of what kinematics means. So in kinematics, we're interested in the motion of objects here without being concerned about the forces that are causing that motion, right? So we're only interested in the motion itself. And as I just mentioned, we can take these same equations that we generated in the linear kinematics case and generate these equations that we see down here, equations 9 through 13, in the language of rotational variables, right? So basically what we end up doing, and it's not quite as simple as just changing every x to a theta, every v to an omega, and every a to an alpha, but instead it's applying these definitions to each of them. So every x turns into an r theta, every velocity turns into an r omega, and every a turns into an r alpha. Okay, and if we do that to these equations, we do end up with these equations here. I'm actually going to go through equation by equation and show how it works. It's really very, very simple. You're basically just substituting in the values, and we find that the r's always all cancel out, and we just end up with these equations. But I'll go through each one of them individually just to show you guys how it works. And then we're going to do an example where we make use of these. Okay, so again, this chapter is really packed with a bunch of interesting ideas, and really all that it is just reframing everything that we've done before. Like we're looking at kinematics. After this, we're going to be looking at dynamics, where we looked at forces. We're going to be looking at energy conservation and energy. We're going to be looking at momentum. So all these ideas that we saw in the past are now going to be rephrased in terms of rotational variables and rotational systems, where instead of dealing with things moving in straight lines, things are moving around sort of on a circular path, right? And so we can basically take any problem we could have done in the linear context, and just by translating over, well, we're going to see it's not quite as simple in every situation, but in many situations, just translating to the sort of rotational equivalent, we can then make up a problem and solve a problem using those tools. So really, this chapter kind of introduces a couple of new ideas, but also basically just doubles everything that we can do, because instead of just being able to do it linearly, now we can do it rotationally as well. Okay, and so let's start off. I'm just going to straight up derive each of these formulas from our original one. So I'm going to start off by writing down all of our equations here. And so we're going to use the idea that x equals r theta, that v equals r omega, and that a equals r alpha to translate all of our kinematic equations over to our rotational kinematic equations. Okay, and so we'll start off with the first one. X equals x naught plus the average v times t. Right. So x equals x naught plus v average t. And if we just go right through and replace the x's and v's, we're going to see that we end up with r theta equals r theta naught, right? So theta naught is going to be our initial angle, where x naught was our initial position, right? Plus, well, v bar is just going to turn into r omega bar, again, because our radius is constant, so the only thing that we need to average here is r omega times t, right? We can see right away that we can just divide out the r's, so we divide out the r's, they all fall out of the equation. We end up with theta equals theta naught plus average omega times t, and that gives us the equation that we see up here. So that's our first equation. We're going to see that they all relate sort of directly like this, right? So we'll do the second one. So average v is 1/2 v naught plus v, right? So we have average v is equal to 1/2 v naught plus v. If we substitute in, for all these v's, we end up with r omega average is equal to 1/2 r omega naught plus r omega, and that looks like a subscript, but it's not supposed to be. There we go. And so we can just factor out both of these r's, and then we're going to find that the r's cancel, and again we end up with average omega equals 1/2 omega naught plus omega, okay, giving us our second rotational equation from up here. Okay. Now let's take a look at our third one. So v equals v naught plus at. That one we use fairly often. So v equals v naught plus at. And so let's make the replacements we need to here. So we end up with r omega equals r omega naught plus r alpha t. Again, the r's get divided out, and we end up with omega equals omega naught plus alpha t, okay, as we have written above here. I'll do the last two. I'm sure that everybody can already see sort of where this is going, but just for fun, I'll do the last two. So maybe my favorite of the kinematic equations, the one that I sort of go to first all the time, will be this one here. And so what are we expecting? We're expecting that equation 7 is going to turn into equation 12, right? So let's see if that actually ends up happening. So v naught t plus 1/2 at squared. And now let's just substitute in for all the rotational variables. So we end up with r theta is equal to r theta naught plus r omega naught t plus 1/2 r alpha t squared. Okay, and we can see again that each of these terms has an r in it, so we can just divide out all those r's, and we're going to end up with theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Now, I just wanted to point out that in the text they go over all these equations again, but they seem to want to write it down with no initial angle now, right? So they write something like this. I think I don't have the textbook open in front of me right now, but I think they write something like this. And so why is this not the same? Well, it really is the same. What they're just saying there is that they've selected their theta naught to be 0, right? So they're just starting from wherever the sort of rotational experiment starts. They're calling that their 0. This form that we have written down, the one that we just generated, is a little more general. You could start with some non-zero theta naught, so I like to use it in that form. But the one in the textbook will suffice for a lot of other things, right? So that's that one. And maybe I'll just do the very last one here. So we have v naught, right? So we have v squared equals v naught squared plus 2a x minus x naught, right? And so what are we expecting to see? Well, we're expecting to see that this is going to turn into this equation here. And let's go through and make the substitutions that we need to. So we have, so v squared becomes r omega all squared. That's supposed to be just a bracket. V naught squared is going to end up being r omega naught squared plus 2, and a is going to be r alpha. Our x is going to turn into r theta minus r theta naught, right? And so maybe I'll do one extra step here. We're going to have to square the brackets, so we're going to end up with r squared omega squared equals r squared omega naught squared plus 2, and I'm going to factor out an r from each of those terms in the bracket. We're going to end up with r squared alpha theta minus theta naught, right? And now we can see that this r squared cancels from each of these terms, and we end up with omega squared equals omega naught squared plus 2 alpha theta minus theta naught. Okay? And so we can see that we have generated the 5 equations that we have listed here. Each of them sort of each of them starts from their linear beginning, and then we build up the rotational version of that equation. Okay, and so it's not important to remember how to do this, although it's very, very simple. You just take the linear equation, make these substitutions, and clean it up, right? But you'll be supplied with these rotational equivalents on the formula sheet of any of the tests that I'll be giving, more than likely. Okay. And so let's take, we could take any idea that we did in any of that first module, where we did any of those kinematic calculations, and translate any of those questions into a sort of rotational version of the question, right? Like I could go through and ask any number of questions, but instead of having this object that we're trying to explore operating in a straight line, it'll instead go around an arc, right? And so we're going to take a look at one example of this, but you can imagine that you could make an almost infinite number of different examples. So this is really a sort of rich area for me to pick from for future tests or exam questions, right? Well, let's take a look at one example here, and you guys will see more in the assignment, and I'm sure more in future tests, right? So let's start off with the first example here. This is from the textbook. This is 10.3, and then they also do 10.4, where they just build on example 10.3, but we're going to do it sort of all in one shot here. And so we have a big fish that's pulling on a fishing line. So we have a fisherman with a fishing line. So the fish is pulling on the fishing line, and line is getting released from the reel, right? The fish is pulling the line out of the reel, and the reel is spinning as the line is being pulled out. So initially the system is at rest, and the reel has a radius of 0.045 meters. And then as the fish starts to pull on this thing, we get to an angular acceleration. So the fish is providing this angular acceleration. The reel is spinning up to speed here at 110 radians per second squared, and it's applying this angular acceleration for 2 seconds. Okay, and we want to answer all 4, or I guess 5 of these questions, sort of given these initial conditions, right? So let's do that here. In part A, we want to find the angular velocity, so omega, of the reel. Okay, and so we'll start out by pulling out one of the equations, one of the ones that we would use quite often, but we're going to write it down in terms of its rotational quantities here. And so let's remember that omega equals omega naught plus alpha t, right? And so we can right away substitute in values. So omega naught, well, we're told that this thing starts from rest, right? So this thing has no initial angular velocity, so that's a 0. And and we know that the angular acceleration being applied to it, is 110 radians per second squared, and this is applied for 2 seconds, right? And so right away we get to a pretty simple answer. Our angular velocity after the 2 seconds is going to be 220 radians per second. Okay. In part B, we are looking for, what are we looking for? At what speed is the fishing line leaving the reel after 2 seconds? Okay, so we want to know what the sort of linear speed that this fishing line is leaving the reel after this acceleration has happened, right? So what we want is v, but we know that v can be written as r omega, right? This is just our linear, our tangential velocity is just equal to the radius times our angular velocity. And we just calculated the angular velocity. We are also given the radius, and so we can write that down right away. And we end up finding that v is equal to 9.9 meters per second. Okay, so that's the answer to part B. I'll box these off. Okay, part C. How many revolutions does the reel make? So we want to know how many revolutions this reel makes in this 2 second period over which we have this acceleration happening. And actually, this kind of reminded me something important that I forgot to mention above. It should kind of be obvious, but it definitely bears mentioning, right? So when we first developed all these kinematic equations, right, these were all only applicable where our acceleration was constant, right? So we have to only apply these formulas where we have constant acceleration. If the acceleration changes, we can't bridge the gap of that acceleration change with one of these equations. We have to find some variables that we can relate between the two parts where there's different accelerations, but there's no way to solve with one equation for two different accelerations, right? So we need to be careful. All these equations only apply where there's constant linear acceleration, constant a, right? And so similarly, all these equations written in terms of our rotational quantities only apply where we have constant angular acceleration. So this only works where we have constant alpha, okay? So we want to remember that and sort of work with it the same way we did for our linear kinematics, right? So we can tackle problems where there are different accelerations, but we have to be very careful how we apply the formula so that we're not using them in situations where we have different accelerations in one formula, right? Okay, so with that in mind, we're now looking for how many revolutions does this reel make during this period of acceleration, right? And for what we did over here in part A and for what I'm about to do here in part C, let's remember that the whole time, the whole duration of this problem, we have one acceleration, right? Until we get to the fifth part of the problem that came from 10.4, which we're going to sort of see how that works. But the whole time that we're dealing with this, we have one angular acceleration. Alpha is equal to 110 radians per second squared, and it is that for the full 2 seconds that we're sort of answering these questions, right? So that means we can apply all of these equations that we generated just a few minutes ago here up here, right? So we can apply equations 9 through 13. And so let's apply one of them here. We know that theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared, and we want to find how many revolutions happened during that time. And so let's do the calculation. Well, we can just set the initial theta naught to be 0. Initially, there was no angular velocity, so we can set omega naught to 0 also. And then we simply end up with theta is equal to 1/2 alpha. Oops, that's 110 t squared, right? So 2 squared. Okay, and if we do that calculation, we're going to find that theta is equal to 220 radians. Okay, and I just realized I haven't calculated this number out, so I'm not gonna pull out a calculator now. But basically, we have this in terms of radians. Maybe I'll come through as I put the notes up and actually finish the calculation up. But we're asked how many revolutions does this sort of give us? Well, we know that there are 2 pi radians in every revolution, so we would need to divide out our 2 pi here, and then we would get the number of revolutions that have been done. But as I said, I don't have a calculator, and I won't try to just do it by hand here, so this still needs to be divided, but basically that's the idea. You have it in radians, you need to get it to revolutions then. Okay, so in part D, what are we looking at? Oh no, this isn't part D yet. Okay, so no, I wasn't able to read my notes, but I did then go through and I did this. So I said 220 radians times 1 revolution per 2 pi radians will then give us a theta equal to 35 revolutions. Okay, so that's great. So we do have the full answer here, and the answer is 35 revolutions, right? Now on to part D. So in part D, we want to know how many meters of fishing line come out of the reel during this time, right? So we want to know what x is basically, right? So we know how much theta has changed. We want to know what x is. Well, we have this handy equation that relates theta and x simply through we simply need to know what r is to be able to get x from theta. And so we can just plug that in right now. What's r? 0.045. And we need our theta in terms of radians here, so that's going to be 220 radians. And this gives us an x equal to 9.9 meters. Okay? And so that's the answer to part D. And do I have space here? I do. Okay, so in 10.4, well, so basically they stop with this example of the fishing rod, and then they reintroduce the fishing rod in 10.4, and they simply ask, what if the fisherman now applies the brakes after 2 seconds, giving it an angular acceleration alpha of minus 300 radians per second squared. So how long will it take for the reel to stop, right? And so we have a new angular acceleration here. So we have to be careful. We can't just bridge the gap of the 2 angular accelerations with one equation. But like we could in the past, we can simply set our omega naught. So what we're going to do now is we're going to set omega naught to the old omega that we found. So before we started off with an omega naught of 0, and we found that at some time t omega would end up being 220 radians per second. Now we're going to set omega naught to 220 radians per second, and we're going to answer this question about what would happen if we slam the brakes on from 220 radians per second, where the brakes here account account for this minus 300 radians per second squared deceleration, right, or negative acceleration, I should say. Okay, and so let's do the calculation. So we have scroll down a little bit. We have omega is equal to omega naught plus alpha t. We're trying to solve for what? We're trying to solve for how long it's going to take for this thing to stop. So let's rearrange this. We're going to end up with t is equal to omega minus omega naught over alpha, and we have all the values here on the right hand side, so we can replace omega with our, well, we want this thing to stop, right? So omega is going to end up being 0. Our initial angular velocity is 220 radians per second, and we have a negative acceleration, or a negative angular acceleration, I should say, of minus 300. If we do this, well, we can see right away this is going to be it's going to be 11 over 15, right? If we reduce it down, But if you want to, you can get the decimal version of that. We're going to end up with a t equal to 0.73. Oops, that looks like a 6, but it's actually a 0.73 seconds. So it takes 0.73 seconds to slow this reel down from 220 radians per second down to 0 radians per second. Okay. There are a number of other good examples in the text, and if you're sort of preparing for the final and you're rewatching this video, these would be good ones that I could ask a number of questions from, so make sure you sort of drill those ones from the text. But for now, we're going to move on before I make this video too long, and we're going to move on to our next topic in this module on rotational motion. Okay, I'll see you guys in the next one.